function. Right, let's look at integration of other functions, and let's start off by looking at the exponential. Okay? Alright, what's going on here? If I move C, so it's my x value, if I move this around, look what happens. Take it all the way up. What's going on? So let me just pause that around about, let's make it at 7. Can I get 7? Right there. When x equals 7, y equals 1095.63. What's going on? So the y value of the e to the x is, how is that related to the area?
It's the same.
It's the same. So if you integrate e to the x, what do you get? You get the same thing. Yeah, and so essentially that y value, when you plug in your x value into there, that y value will give you that total area underneath it. Yeah. So let's put that in and look at the possible variations we can get as well. If I just do view, let's put some line paper in. Okay, and we know that if you differentiate e to the x, you get e to the x. Therefore, if you integrate e to the x, this simply gives us e to the x plus c. Okay. What about if we were to change that into e to the kx? What's that going to give us? E to the kx. Yeah.
E to the kx divided by k plus c.
Okay. Here's a question. Would it be e to the kx, we've got the plus c there, would the k go here or would it go at the bottom?
Go.
Hands up to the side. Hands up if k goes, hands up if k goes to the bottom. Hands up, why does it go to the bottom, Erisa?
Because you divide instead of times by the power of
Okay, right, yeah. So you divide by, okay. And
integration.
yes. Another way to think about it, if you're not sure, when you do e to the kx over k, if you were to differentiate this, okay, we know that gives you k e to the kx over k. That power here has come down. We've differentiated this part, and so those k's will cancel, and that gives you e to the kx, which is what we started with. So you can always differentiate your answer. Remember what I said, those of you I had in the first year, that if you've got some sort of function, say it's fx, when you differentiate it, you're going down, and then so when you differentiate, you go down, and when you integrate, it's basically the reverse process. You're going up. So d over dx takes you down. From fx, you get f prime x, and if you integrate f prime x, it gives you fx. All right. So, given that, let me give you a little problem. Can you have a go at doing this question here? Let me put it up. I'll give you about 2 minutes. Off you go. So, let's go over this. We've got 0 to e to the x, which is really e to the half dx. This gives us e to the, we can multiply the powers, so that becomes x over 2. And let's write that as that. When we integrate this, we've now got e to the x over 2, and what happens to this coefficient? What does it become then? It's over a half. Something divided by a half is the same as multiplying it by 2. Is that okay?
Don't you add one to the power?
No, not in this form, not e to the kx. Okay, and so remember, if I've got 1 over a half, that's the same as 2, and you can write that as a fraction if you want. So we've got this. Now we should use our square brackets and put the limits in, and that gives us 2e to the 1 take away 2e to the naught, which is equals 2e take away 2. So well done, Rabia.
And then, yeah, 2e to that.
Let's now look at the area of 1 over x, and let's just look at a couple of findings. So here's a table. A is in my value of x. So here a equals 2, and here's my area. And I can increase this as so, and then look at the total area underneath it. Okay. What I'll do is I'll take a little picture of this and put it in as part of our notes with a couple of questions. I want you to think about what's going on here, and I'll give you a minute to think about it. So let me just put this in. So we've got our values there, and what I'd like you to do is think about the following questions. Number one, what is special, or what do you notice about the area of 2 plus area 3, 3 times area 2, and 2 times the area of 3, and area of 2 plus the area of 5, and which area is going to give you 1. I'll give you a couple of minutes to think about that, and then we'll discuss. Off you go. Alright, area 2 plus area of 3, what does that give you? So this area plus this area gives you what? If you do the area of 2 and you add it to the area of 3, what do you get? You get area of 6. Okay, good. If you do 3 times the area of 2, what does that give you? Which area does that correspond to?
9.
Yeah, we'll come on to that in a second. Does it give you the area of 9? Is that what you found?
Area 2. Area
Oh, sorry, no, 1.
area
Which area does that give you? 3 times the area of 2. So you take this, times it by 3.
3 times area of 2, so 3 log 2 is log 2 to the third, so power of 3, which is 8.
Alright, thank you.
I've written them in points.
So, here we've got the area of 8. 2 times the area of 3 will give us the area of what? 9. Good. What about the area of 2 plus the area of 5? Tess, what does that give us? Anyone?
10.
Yeah. Okay. So all right. Now here's a trick. Well, it's not a trick question. If everyone gets this, it'll be brilliant. Which value of A do you think you'll get an area of 1?
2.5. 0.
So when A equals 0, the area will be 1. Think about what you just said. That means when here at this point,
1.
we're starting from 1. Don't forget. Yeah, this is from 1 to 2. That gives you A2.
Is it area 2
2 point.
No,
2.71. Let's have a look. Okay. Let's have a look. So we all agree it's some sort of logarithmic expression. It's following log rules. You can see that happening. Let's now see where you get the area of 1. So I'm going to bring this down, and bring this down, bring this down,
2.3.
It's 8.
and bring it down further. It's about 2.7.
E.
Yeah? Okay, good. So it's E. And so that means, what does that mean then? What we do know is that the area of A is the log of A, but it's to the base E. So therefore we can write this as the ln of A. Okay, so the area of underneath that 1 over x graph follows a logarithmic pattern, and therefore it gives us, if you were to integrate 1 over x dx, you'll get from 1 to a, you'll get the ln, sorry, you get ln x or ln a in this. Well, let me just do it without the limits. So here you just get ln x plus c. Okay, so we've established that. You can look at here of the graph and see that for yourself. However, there's a bit more to the story. If we look at the graph of 1 over x, or in fact, before we do that, if I have, that means if you differentiate ln of x, what would you get? 1 over x. Agree? Okay. What about if you differentiate ln of minus x? What is that going to give you?
1 over x.
Why does it give you 1 over x? Go on.
Because you can only take the modulus of x. Ln can only be taken in positive values, so you have to.
No, but let's leave that discussion out. What do you, if you use a chain rule and differentiate this, what do you get?
-1 goes to 0. So
The minus 1. So if that's ln u, that will give you 1 over u, which is minus x, and then you differentiate u. U is,
-1.
that gives you minus 1, and therefore that gives you 1 over x. That's this chain rule. No, without getting into the discussion of modulus, you can only take the positive, all that business. Just use the chain rule and differentiate that. Okay, that's what I'm saying. And therefore that gives you, we've seen it here, you can see what's going on here using the chain rule, you get 1 over x. And therefore, what we're saying is that this is true for x greater than 0 or x less than 0. This result here is true for x greater than 0 or x less than 0. And therefore what we can do is combine both of those results, the positive and the negative, into a single expression by saying that you'll take ln, the modulus of x, in other words you take the positive value plus c, and that modulus combines both of those results, where you can still take a negative value of x, okay, and it'll still work, or you can take the positive value, you still get the same answer. Both of them are fine. However, there's something to be aware of. In fact, let me just put that in a little box, because that's our second result so far. So just to reiterate, our first result at the top was e to the kx is e to the kx over k plus c. And now we've got a second result, which is 1 over x dx, because ln x plus c. Now before we move on, just something to be aware of is, just like we discussed in the homework, where we had 1 over x squared, I think it was. Over here we've got 1 over x. Can we integrate from -1 to 3? Is that possible? Can we do that? What's the problem with doing that?
1 over 0 is...
Right, so 1 of 0 is undefined. And because it's undefined, that process doesn't stand. Yeah, you can try and do it other ways by working out certain limits or approximations, but that's beyond the scope of what we're doing at A-level anyway. Okay, let's now look at an example. Could you have a go at doing, let me put this in, and have a go at doing this question here. It should take you about a minute, but what I would say is leave out 1, don't do that one, just do part 2. As you could do part 1 as an extension if you want to, but I'll give you about a minute to do the first one. Off you go. Over it. So, what do we have? What sort of answers? Let me just get somebody else. What did you get? Jack? 3 over 3x. Okay. Anybody else? Yes?
1 over 3 ln 1 over 3x plus c.
1 over 3 ln 1 over 3x plus c. Okay. Anybody else? Okay. Derek's table?
3 over 3x plus c.
3 over 3x. Okay. Let's have a look. What we could do, with this one is firstly, just take the factor of 1 over 3 out. So we're left with 1 over x dx. We know the integral of 1 over x is simply the ln of x. That's all we're doing. Okay, so and this is an insight. You can see all you want is 1 over x. If there's a 3 in front, you can just take that out, and then you're just left with that. Yeah.
But if you do substitution, you said like 3x equal u, and then you'd have 1 over u into du over 3.
Yeah.
It's a different answer. Why?
So Rabi's raised this question. If you've got 1 over u, where u equals 3x, then you know du over dx equals 3. So dx equals du over 3.
Yeah.
So that gives you 1 over 3, 1 over u du. So that's still 1 over 3 ln of u plus
dx.
c. So we've integrated.
Yeah.
Now if you convert back to this, you get 1 over 3 ln 3x plus c. And I assume she's asking, how comes that 3x is not this ln x? How comes I've got an extra 3 in there? The reason being, don't forget with logs, that ln 3x can be separated out into 2 different parts. We can write that as 1 over 3 ln x, I've used a bracket here just to emphasize that I'm separating the same thing out, plus ln of 3. And then I've got a c. And all I've done is added these two. These two essentially become your constant. You can call it c2 if you want. Plus your ln x 1 over 3. So essentially they are the same. Okay, because that constant is all it is just a number. But as you see in a minute, there's another way to do this, and that's to look at the pattern which I'm about to show you of the generic form that leads to the ln of x. Let's just in order to show for me to show you this pattern, let's look at an example. Say I had an integral where I've got x plus 1 over x squared dx. And we use some substitution where u equals 1 plus x squared dx. Oops, u equals 1 plus x squared. We know du over dx therefore equals 2x. And therefore du divided by 2x equals dx. Is that okay so far? Happy? We can then do this integral from substitution. We know that you've got x over u times du divided by the 2x, and you can see straight away that this x here is going to cancel with this. And to tidy it up, this 2 at the bottom, we can just take that outside, and we've got a nice 1 over u du, which we can then integrate as a half ln u plus c, and then bring the u back in, so you've got ln of 1 plus x squared plus c. Alright, now let's discuss what's going on. Can everyone look up, make sure you're paying attention. Right, the first thing is, normally with ln u, I've always said to use the modulus. How comes I haven't used the modulus here? Why didn't I use the modulus?
X squared is going to be positive anyways.
Exactly. X squared plus 1, okay, is always positive. So there's no need for me to put a modulus sign there. Okay, I'll write that. Therefore, no need for my modulus sign, those 2 straight lines, because it's always positive. You're not going to get some value that you put in where you'll get a negative value. X squared plus 1 is an x squared graph shifted up by 1. Y is always going to be positive no matter which x value, positive or negative, you put in. So that's the first thing. The second thing is, pretend now I change this around. Guys, watch this. It's a little trick. If I make this, you can see what's happened. The bottom part, when you differentiate, gives you 2x. Yeah? So you get this 2x. And you can see I've got an x at the top, and so it's going to cancel out. If I had an x squared at the top, would that work? Would the cancellation work?
But you still be left with an
Yeah, but it wouldn't cancel out. I'm still left with an x, which would be a tedious problem. I've then got to rearrange again and work out what I'm going to do with that. But it hasn't cancelled out. The x's haven't cancelled. What about if I had an x cube? Would it cancel out? Okay. What if I just had, I don't know, a 2x? Will the x's cancel? Yeah. They will cancel, isn't it? Yeah, because all I've got x squared at the top, differentiates to give me something times x. I've got x at the top, it's going to cancel. What if I had 12x? Will it cancel? Will the x's cancel? So at the bottom, I'd have 12x here. I've got 2 there. Will those 2 x's cancel? Yeah. Okay. Then let's get rid of that. Callum.
As long as the power of x on the bottom is 1 greater than the one on the top, it's always going to cancel out.
Excellent. Look what so Callum's just said. As long as the power at the top is 1 less than the power at the bottom, it's going to cancel. So at the bottom, if I had an x cubed, and at the top I had, what would I need at the top? X squared. Tadas, do you see that? Right? So as long as it's 1 power less, when I differentiate the bottom, it will cancel out the top. Yes?
Once you had like an x cubed on the bottom and an x at the top.
No, because what's going to happen?
No, but what would you do?
Alright, but then if you differentiate that, okay, at the bottom you'll get an x squared. With the top you'll have 1x cancelled off, and you will be left with an x by itself. So again, the x's don't cancel. Okay, when you do this little switch. And so what we can do, and notice when it does cancel, okay, we're left quite nicely with this expression, the ln of u. And what we can therefore say is that when you're integrating a fraction that looks like this, where you've got fx at the bottom and f prime x at the top, and you put dx, when you're integrating this will give you, for the reasons we've just discussed, the ln of fx for modulus sine plus c. And let me just put so that's our third result for the reasons we've just discussed. Okay, because the denominator, when you differentiate it, gives you some form of the numerator. When the numerator is in the form of the differential of the denominator, then we end up with ln of fx. Okay, because by the chain rule, you can find that. We'll cancel out. Let's now apply that to a situation. So I'll do one and then I'll give you one to do. So if I just do as an example, say we had to integrate e to the 2x divided by 1 plus e to the 2x dx. Okay, so we had to do this. As a side note, let's just differentiate 1 plus e to the 2x. When you differentiate this, what's that going to give us? 2e 2x. Hands up if you agree. Guys don't agree? Do you agree?
No.
Right. 1 plus e to the 2x. So you differentiate the 1, what does that give you? Nothing. Good.
Oh, yeah.
Yeah? Okay, agree now? You guys agree? Alright. So we know that's what you get. Now the first question to ask is, you know your numerator, the top part, is it in this form? Is it the same skeleton? Is it in that form? It doesn't have to be exact. The numbers don't make a difference. It's just your x parts. Is it some? Does it look like? Let me use a highlighter. E to the 2x. Do I have some sort of e to the 2x at the top? Yes, I do. And so therefore, what I could do is simply write down what I've got. So I'm going to do this by inspection. This is essentially inspection. 2e to the 2x divided by 1 plus e to the 2x. So that means if I integrate this, where this is in the form of f prime fx divided by fx dx. So that's what I've got. I know that this is going to give me ln of 1 plus e to the 2x plus c.
Is there no
Okay. But, hang on. But we know the original question that we started off with didn't have this extra 2 over here. And in order to turn it into the expression, what we could do, any suggestions? Hands up. Not the same hand. Derek to
We can divide the whole thing by half.
yes. I can stick a half there and stick a half there. And therefore my first integral is essentially a half ln 1 plus e to the 2x plus c. How comes I'm not using square brackets for the modulus? Thomas?
What?
How comes I'm not using square brackets for the modulus?
Not sure.
Tadas, do you jump in? How comes we're not using square brackets for the modulus? E to the 2x plus 1 is always above the x-axis, yeah? It's always going to be positive, and therefore you can't get a negative in there. Is that okay? Alright, let me leave you with what I'll do is I'll show you one more set of results, and I'll leave you with various examples and just let you work at your own pace through these examples. Okay? So this is dead easy. Well, let's put this up. I think some people are still copying down. So the next part is just looking at trig functions. This should be quite straightforward. If you integrate sine x, what are you going to get? Arisa? Cos x plus c. Will that be plus or minus, Irina? So if I integrate sine x, will I get cos x or minus cos x? Cos x. Yeah. Is it? So if you differentiate cos, do you get sine? You get minus, isn't it? So therefore, if you integrate the sine, that should give you minus cos x. Excellent. Okay. If you integrate the cos of x dx, what would that give you, Tez? Excellent. And then finally, if you integrate, who remembers what you get when you differentiate tan x?
Secant square x.
Sorry?
Sec squared x.
Okay. Sec squared x dx. Okay. Now what we could do is take those results and simply put in a constant. So therefore, the integral of sine kx dx equals minus 1 over k cos kx plus c, and therefore the integral cos kx dx, but I don't need that bracket there, dx is simply equal to 1 over k sine kx plus c, and sec squared k kx dx will just give us 1 over k tan kx plus c. Okay. Right, let me leave you with a couple of questions which you can now do to work with to apply these. I've put this in a red box to emphasize these are our final set results, and let's stick in a couple of questions and I'll give you the final answers so you can check. Okay, let's do example 5. Now have a go at that. And yeah, sure. Just give me a second. Let's insert Example 6. Okay. Okay? Is that better? Alright, I'll leave you with the final answers so you can just double check if you've got them right or wrong. What I'd like to do is work for example 5 and 6. And this is what you should get. And then we'll go over it if needed. Let me just put that in. Jack, you got a question?
Why was it 1 over k?
Alright, because if you use the chain rule to differentiate 1 over k tan kx, or maybe start off with, look at 1 over k sine kx. If you use the chain rule to differentiate that, what would you get? I would literally write that down and differentiate it using the chain rule. Yeah, k cos kx. And so those k's will cancel, so you've got k at the top, k at the bottom, and so you'll be left with cos of kx. Yeah? And so the reverse holds true then. If you integrate cos kx, you'll get what you started with, 1 over k sine kx. Is that okay? So 1 over 3 sine cube x plus c. And last but not least, this should give us minus 1 over 3 cos of 3x plus c. Okay, so let's do example 5. Let me just copy this and I'll bring it down. And let's go over example 5 together. So over here, just to double check, the derivative of the numerator, so if we just differentiate the bottom part, 3x plus x cubed, that just gives us 3 plus 3x squared. And if we factorize this out, that will give us 1 plus x squared. And all we're asking is that in the form of the numerator? Does it look like? Is it the same skeleton in terms of not the numbers necessarily, but the x parts? So in here it's an x squared. Is it the same skeleton? Yes, it is. Okay, and therefore, if that's true, then we can approach this in two different ways. One is just to say that one way is just to say that if we were to integrate 3x plus x cubed and with our integral at the top, 1 plus x squared dx of 2, 1. We know from the log rules that will give us ln of what we've got at the bottom, the numerator, 3x plus x cubed. Okay, and we've got 2 and a 1. So that's true because it's in the form of f prime x over fx. Okay, so this is this form here. However, in our original integral, we don't have this 3. This is an extra 3. So in order to balance this out, we can just simply multiply both sides by 1 over 3. Now we can substitute the values in, keep the 1 over 3 outside. Okay, that doesn't need to get involved. And we've simply got the ln of 2 times 3, which is 12, plus 2 times 3, which is 6, sorry, plus 2 cubed, which is 8. So that gives us 14. Take away 2 times 3, which is 6, plus 1. Sorry, then take away ln 4. So 1 times 3 plus the 1 is ln 4. And that's the same as 1 over 3 ln 14 over 4, which can cancel down to 1 over 3 ln 7 over 2. But look how it all starts off. The whole point behind this is I'm looking for something that is in the form of f prime x over fx. That's what we're looking for. And so we can set the integral up and then balance it out in order to match the original integral that we've been given. The modulus brackets, yeah, so when you integrate f prime x over fx, this will give you the ln of f of x with a modulus bracket plus t, because it's saying it accounts for both the positive and negative values of x. However, if you know a case where the outcome y cannot be negative, then there's no need to put modulus brackets in. You can say it's always going to be positive anyway. Okay? But just take the modulus, don't overthink it. It's just the standard result. It's what we discussed earlier, and that's what you get.
So if you put the modulus brackets in when it can't be negative anyways, do you lose a mark?
I doubt, no, I very much doubt you would lose a mark for that. Yeah, it's a standard result. You haven't technically written anything wrong. You just said it's modulus of this, which is still the same answer. You haven't given the wrong answer.